Hi. So in this part of the section, we're going to go ahead and talk about calculating and interpreting z-scores. And we're going to go in a little deeper and touch the surface on a little more deeper concept, the empirical rule afterwards. So z-scores come from the idea of standard deviations and average from the mean. We talked about one standard deviation is that give or take from the mean, right? The average distance from the mean. And so now, what if I was two standard deviations from the mean? So I'm two averages away from the mean. Or how about 3? Or how about 1.1, right? So the z-scores are in context of average distances from the mean. However, z-scores are measuring different distributions. So z-scores can be negative, but the idea is that they are average distances from the mean, but we use the integer part of the z-scores to determine comparing different distributions. Just like the three sections that we saw that had all the same average and medians, but their spread was different because the scores were different. How do we compare those three sections of quiz scores that all had the same median and median? Well, we looked at their spread, right? One had no spread because they were all scores of 5. The second one was spread of 5 points, and the last one, section C, was a spread of 1 point, right? And so which one had the most spread, right? Well, that one that had the standard deviation of 5. And so how do we measure those distributions and compare them correctly if their standard deviations are different? Well, this is why we need z-scores. So z-scores can take things and what we call normalize the data. And so z-scores can be negative or positive, and wherever it's more positive, obviously is the higher score, I would say, or larger data value comparing all distributions. So we're taking different distributions and comparing them by normalizing them into what we call a z-score. So let's go ahead and take a look. It's a really simple formula too. So the formula here is going to be just whatever data point you're observing minus the mean divided by the standard deviation. If it is a population, it uses the population parameters. If it's a sample, it uses the sample statistics. But essentially all you're doing is the difference divided by the standard deviation. Notice that we use the non-resistant statistics, right? The average and the standard deviation. So they are heavily influenced by outliers, right? So we use those. That's why we're normalizing them. So let's just say I had a mean score on a test for a stats class, an 82, and a standard deviation of 7. If a grade A is 93 points, what is the z-score for an A on the test? So the z-score will normalize this value. Watch. So the z-score will be the x minus the x bar over the s. So what data value are we observing? Well, the value is 93 points, right? Because we're looking for what the z-score to get an A. Minus, and what was the average? Well, the average is going to be 82. And we're going to divide by that standard deviation of 7. So if I put this in my calculator, right, I could go to my calculator and put 93 minus 82, close it. Remember, I always use parentheses around my numerator and denominator, and divide by 7. And I get 1.5714, blah, blah, blah. But I'm going to go ahead and round to 2 decimal places here. So I have 1.57. There's the z-score. And so notice that the z-score is positive here. So let's make a note. So when z is positive, this means the x value you're observing is above the mean. Okay, so when z is negative, this means that x is below average. So a score of 93 means that it's above the average, it's positive. If a z-score is negative, that means that score is below average, and it should be negative. All right, so if I wanted to use the z-scores to compare distributions, then I can do this example about with Pat taking her midterms, right? So she received an A in statistics. She received an 82 on her stats, a 72 on biology, and a 91 on kayaking. We automatically see the 91 and we think, oh, she did the best in kayaking. Well, not really, because there are three different distributions. What if the average is a lot higher? So if we look at the kayaking score, we can see that the grade of the average was really high as well. It was close to an A. So the average score in the class was almost an A, and she got an A. So did she do that much better than the average? Let's say on her stats exam where she got an 82 and the average was 74. Well, she did do above average there, definitely, and kind of far away from the average. 72 on her bio and 65 was the average. So 65 was pretty low, is a low average, and she was above that. So we're going to see where did she score the farthest above the average, right? So the only way to do that is to standardize it. And so we're going to go ahead and standardize or normalize. That's the idea. And we're going to find the z-score for each exam. So we're going to find the z-score for each exam. Okay, so the z-score for the stats exam is going to be equal to 82 minus 74 divided by 12. The z-score on our biology exam is going to be 72 minus 65 divided by 10. And the z-score on our kayaking will be 91 minus 88 over 6. Okay, so if I just put these in the calculator, I'll get 0.67 for the stats class. The z-score for the bio exam will be 0.7. And the z-score for the kayaking will be 0.5. So if I look at all these three values, which one is the farthest to the right? Which z-score now has the highest distance from the mean? So if I went ahead and drew a number line, okay, so here is 0. This is where the z-score is 0. Here is z-score equal -1. Z-score equal -2. And over here, z-score is 1, z-score is equal to 2. Okay? So notice those are just integers, right? So over here means that z-scores are negative and it's below average. Over here, it means that z-scores are positive and it's above average. So where did Pat score? Let me just mark them with like an X. So with their letter, right? So 0.67 would be here. 0.7 would be here. Oops. S, B, and then 0.5 would be here, K. So which one was the farthest to the right? Which one had the farthest distance from 0? The bio exam. And so we would say that we thought the kayaking, right? Because we got a full solid A on that. But it wasn't really that far from the average. And if we look at the bio exam, I think that was the farthest from the average, right? And so we would say, that Pat did relatively better on the bio exam. That's how we talk about it in context of conversation, because it's relative to the other two exams. If I took all her exams she took her whole entire life, who knows, right, where that would lie. But in this case, it's relative to those other two exams. We're comparing three distributions with three different averages, three different standard deviations. How do you know where she really did better? Well, we need to normalize it. We need to standardize it into z-scores and see where she scored farthest from the mean, right? How far above average did she score? So the idea of this number line that I have here comes from the empirical rule. So if I keep this up here on the window and then I see empirical rule, notice this is the same thing. Here is where the average, and there's no distance. So z is equal to 0. If I'm one standard deviation away from my mean, z is equal to -1, +1, right? If I'm 2, I'm -2, +2, and then so on. And usually we're not more than three standard deviations away from your mean. You might as well just start over. You don't have to, but you could start over. And so you're pretty far away from your mean. And so the z-scores here are relative to the average, right? And so notice that no matter what these values are on the x-axis, the z-scores remain the same. Notice I have solid numbers here, and no matter what, these z-scores will not change. But because distributions change, the mean and standard deviation, that x-axis will always change according to your data. But z-scores will never change because those are fixed for each of those corresponding tick marks. And we like this because one standard deviation away says that 68% of your data lies in there. Here, two standard deviations away say 95% of your data lie within those two values. And then three standard deviations away tell you that 99.7% is within those two values. So 3 standard deviations away is almost all of your data, guaranteed. It's not a question. You can go any part of the world, 3 standard deviations away, almost 100% of your data. That's it. And then 95% means you would add and subtract 2 standard deviations away, and you're guaranteed that 95. Now, more may contain in there, but this is just a guarantee. If you have a million pieces of data, at least you know 95% of your data will lie between these two values. And same thing with 68%. So even though, like, I have examples where we do the empirical rule and we show 3 standard deviation way actually contains all my data in my set. Well, yeah, but if I had a million pieces of data, I really wouldn't know that. And so these 3 rules are really nice, with large sets of data. And we're going to talk more about that in the future because we're going to be using this empirical rule a lot in this class. Now, there is a different rule that's very close to the empirical rule. The empirical rule is the most popular, but there is Chebychev's rule. And that's essentially the empirical rule, except the percentages are just a tad different. Here it says that you're lying within 2 standard deviations, that's 75% of your data. So notice 2 standard deviations was 95% would lie between those two values. Chebychev's rule says that 2 standard deviations away, 75% will lie within those two. 89% lies within those two values, 3 standard deviations away. And if you're 4.5 standard deviations away, 95% of your data will lie within there. And the only difference is the shape of the distribution. So the empirical rule only holds if the distribution is bell-shaped. It has to take on this bell. It has to. Whereas Chebychev's is for any shape. So Chebychev's rule is pretty powerful for the fact that it found these rules for any shape. I don't care what you look like. You're skewed left, skewed right, you're uniform, or your bell shape. Chebychev's rule is guaranteed. If you know that your data makes this nice bell shape, then you're guaranteed to have tighter intervals. And it just depends. If you don't know the shape, then use Chebychev's rule. If you know the shape of your data, use the empirical rule if it's normal. It's that easy.